Right, so hello. If you are in Chem 30, you might have already done an equilibrium acids and base unit test, or it might be coming up. I know my class has already done it, but I'm tutoring a student right now who asked me if I would do this review as a video. It's a bit long, so I'll do half of it today and then finish off the other half tomorrow. So let's go through some of these questions. So this is just part of a review package. It's a pretty common one you can find online. So starting with the first one, showing that you know what an Bronson-Lowry acid is. So it's just something that can donate a hydrogen. So definitely in the reactant side, water is the one donating a hydrogen. And on the product side, your HOCl is donating the hydrogen. So when we're looking at the first one, the answer is D. The next one asking what is a substance that can act as an amphiprotic species. So amphiprotic is either water or a substance that has a hydrogen to donate and a negative, meaning that it can accept a hydrogen. So when we're looking at this one, the only choice we have is B for water. Looking at number 3, the two species in equal molar amounts that could act as a buffer in this solution. To be a buffer, you have to be a weak acid and be beside its conjugate base on your data booklet. So when we're taking a look at that, you know, we can take away a few of these because it's either strong or not the conjugate. So the only one that would work here is A. Moving on in number 4, in the bleach solution. So part of this information up here, it does tell you the pH of the solution. So the pH is 10.87. So if you have a pH of 10.87, and then you take a look at your data booklet, and just going through the choices, phenolphthalein would be colorless. That's not true. That would be pink because it's base. B, talking about Arzenium yellow R would be orange. This one is true. This one, our range is between 10.1 and 12. And you can take this, take a look at this on page 10 of your data booklet. And the color, if it's below 10.1, would be yellow. If it's above 12, it is red. So if our pH is right within that range, it would be a mix of these two colors, which would make orange. So your answer there was B, and you can just also take a look at the last two to rule them out. This question here is asking to calculate KEQ. So we would need the KEQ or KC expression to start. So we would have our products, and then if you have a coefficient, it becomes our exponents over reactants, and we can keep everything because everything is in the gas stage. So just be careful here to not include solids or liquids unless everything is a pure liquid. So once we set up the expression, then we can go ahead and plug these values right into the expression. And if we do that correctly, you should see your answer be 2.14. Question number 5, asking to be able to increase the concentration of CO3. So CO3 is here. The first one says raising the temperature. It's an exothermic reaction. So if we had temperature, it would be on the product side. If we add in, it's going to shift away, which would decrease CO3. Adding a catalyst won't do anything. Removing SO2, if we take this out, it's going to shift to replace it. Again, using the product step. So that's not going to work. What we can do is directly add in NO2. So adding this in, you're going to shift away, increasing your products. So that is your answer there is D. Moving on from here, number 6, which of the following solutions would have the lowest pH? So to be the lowest pH, you want to be the most acidic. So I just took a look at my data booklet and I can see that my strongest acid is H2SO4. And then I would look at my concentration. The one that is more concentrated would be more acidic. So here your answer is C. Moving on from here, sorry about that. Let's fix this. Number 7, it's giving you an expression equilibrium and then telling you that the rate of formation of the Pn negative, if you are in equilibrium, would be equal to, I just said it, equal to the rate of formation of one of the reactants. So if you're in equilibrium, it's all about the rates. The rate of the forward equals the rate of the reverse. So your answer is D. Question number 2, you're given, or numerical response number 2, you're given the concentration of the H3O positive ions and asked the pH of the wine. So in this case, you just have to do the negative log of that concentration and go directly to your pH value, keeping 2 sig digs because we have 2 there. So that would be 3.49. And because this is a pH, the significant digits are the ones after the decimal. Moving on to number 8, if the following components of acid rain is of equal concentration, then which of them would have the lowest pH? So this is another question. If you're the lowest pH, you are the most acidic. So if I look at page 8-9 of my data booklet and I wanted to see which one is my strongest acid, it's going to be D. Looking at this next one, the Kc expression, this is setting up the Kc expression and just knowing that unless every single state is a pure liquid, we do not include it. So the one that shows us products over reactants without water included was D. This next one, you have the concentration in a 0.05 mole per liter of H2S solution. If we want the concentration of the hydronium ion, we're going to use that Ka formula, which is your hydronium ion concentration squared divided by the concentration of the weak acid. And we can minus hydronium, but this is one of those instances because it's so small based on that ice chart and that setup in the theory. If it's in the denominator, you can ignore it so that we can find it. So the Ka value, we're going to take a look at your data booklet, and the Ka of H2S is 8.9 times 10 to the negative 8. We're solving for the hydronium ion. That value was squared, and we're going to divide it by the concentration of the weak acid. So we're just going to isolate hydronium by multiplying both sides by that 0.05. And then once you do that, you'll get a value on the left-hand side and just square root the whole thing. Once we do that, you would see your answer is B. Next one, an equilibrium that would favor the products. If it's products being favored, your acid would be higher on the table than your base, looking at page 8-9, and the one that would show you that is C. So if you take a look at your acid here, it's going to be higher on the table than your base, and that would make products being favored. If you check the other ones, your base is higher than your acid, so that would be reactants being favored. This example, numerical response number 3, asking for the conjugate base of the ammonium ion. We will need the Ka of the ammonium ion, and then we can use the Kb formula is Kw divided by Ka and just plug in those values. So 1.0 times 10 to the negative 14 divided by 5.6 times 10 to the negative 10, and you will get 1.79 times 10 to the negative 5. So filling in your numerical response would just be 1.79. Number 12 is just showing that we still know Chem 20, and that is figuring out the pH based on this concentration. So we know that we just have to take the negative log of that value to get the pH. When you do that, you will get 1.70. And then once you have the pH, if you take it away from 14, you would have the pOH. So the one that lines up here is C. Question number 13, having ammonium nitrate dissolve in water. If you take a look at what's present, we have NH4 positive, NO3 negative, so an acid, a base, and you have water present as well. In this, your strongest acid is going to be the ammonium ion, and your strongest base is going to be the water. So when we're doing this, because we don't see this one here, we'll only have that acid present, your solution will be acidic. Moving on, we have information about a system in equilibrium, and then we have this carbonic anhydrous above, and it's asking in this system, what does that do? It is acting as a catalyst, and in an equilibrium system, it just helps you reach equilibrium faster. Okay, this one, I'm just gonna zoom a bit here. We just want to be able to take a look at what's reacting and match the graph with what's being reacted. And each of these is being reacted with, so if you have an acid, you're reacting it with a strong base. And if you have a base, you're reacting it with a strong acid. So what we'd want to recognize is the first three are acids. So the last one is a base. And if you did take a look at Na2 and S, and you dissociate it, you'd have S to the -2. So that's a diprotic base. So the only one that would make sense for that one is number 3. Now looking at the other three, this is a little bit confusing because of how it's written, but when you have that COOH, it is the H that can be donated. So the H at the end. So in this one, we actually have 2 H's just because the first part is written backwards. So that is showing, again, something diproduct. So you'll have more than one equivalence point. So the only graph that shows more than one equivalence point is graph number 1. And then to tell the difference between graph 2 and graph 4, we can take a look at the strengths, because HNO3 only has 1 hydrogen to donate, and our second one only has 1 hydrogen to donate. So both of them are going to have just 1 equivalence point. But what changes here is knowing that HNO3 is a strong acid, so its starting pH would be closer to 0. And CH3COOH is a weak acid, so its starting point would be a little bit higher up. And that's how we can tell the difference between those two. So we have 2 and 4. Oops, there we go. This one is just a theory question. So question number 15, you have some information about some acids and then asked if they're strong or weak. So if you take a look at your data booklet, the strongest acid you have that still has a Ka is an exponent of 10 to the -2. Other than that, anything above that is considered fairly large. So we know if it's fairly large, it's a strong acid, but this value is also fairly large, 5.1 times 10 to the power 2. So our 2 strong acids are C. Again, take a look at your data booklet, page 8, 9, and just compare what you're seeing in terms of what weak acids are. Because in this question, it is most common to know to pick that first one because it is going to be very large as a Ka, but we just want to take a look and realize that that second value is also very large compared to what's given. Number 16, in the equation given, so our equilibrium, one conjugate acid base pair is. So to be a conjugate acid and a base, you must be weak and you must be beside each other on the data booklet. So page 8, 9, which means you're the difference of just 1 hydrogen. So taking a look at this, you can rule out this first one because that is strong. Again, that's not even related. And then this last one, I believe it's C. I just want to double check it. Number 16, yes. And why? Oh yeah, this isn't even related, so we don't have to pick it. So our only possible answer here is C. Okay, so looking at number 5, when your solutions are ordered from most basic to least basic. So here I'm still looking at page 8, 9 of my data booklet, but when I look at my data booklet, I know that my acids are strong on the left and get weaker as you go down. So that's your acids. Your bases, on the other hand, are strongest on the bottom right and get weaker as you go up. So when you're looking at the most basic, you would want to see what you would find first, what's strongest, and then how they get weaker. So OH is our only strong base. So number 4 would be that first one. And then number 3 is an acid, so that would be our least basic because there's no basic part of that acid. And then these last two, it's just going to be placement. So when you take a look at your data booklet, which one is this? 2 is higher than lower down than number 1. So the order here was 4, 2, 1, 3, just looking at our data booklet. This question is giving us a picture and then asks which best shows that your buffer system. So HA is your weak acid. So if HA is a buffer, then that means as a base, it's losing a hydrogen, right? We're the difference of 1 hydrogen. And we also know to be a buffer, you are not able to have anything strong. So with beaker number 1, that would not be a choice because we don't have the base part of the buffer. Beaker number 2 is also not a choice because they're adding in hydronium and we cannot have anything strong when we're looking at a buffer. And then beaker number 3 and 4 work because it's exactly what we need within the beaker. So that answer is D. Which of the following mixtures could act as a buffer? Again, to be a buffer, you need a weak acid with its conjugate base. And when we're going through this, you do have a few that are not even related. Like this first one, you have too strong, right? A strong base, a strong acid, that's not going to work. In the second one, they're not even related again. In the third one, not related. And so in this last one, if you dissociate this, you'd see that you're a difference of 1 hydrogen and you're beside each other on the table. Numerical response number 6. If you wanted to calculate the Kb, using that Kb formula, you have your hydroxide ion squared divided by your weak base, and then you would subtract hydroxide if you have it. So when I do plug this one in to the formula, I'm just plugging in the values to what I see and then doing the calculation. And what I would get here is 9.24 times 10 to the negative 6. So filling it in for as A, B, C, D, it would be 9246. Number 10, talking about acid rain going into lakes and rivers and how it affects them. This would be an environmental concern. I find you don't get asked that quite as often anymore in the diploma, but still, I feel like it's also common sense, so hopefully it would be easy enough to figure out. Number 20, if you have thymal blue indicator and it in its blue form added to H2SO4, and H2SO4 is a strong acid, what we would show here that it would turn red because that's the color of the indicator in an acid if you look at page 10 of your data booklet. And your indicator is able to, and this one would be able to gain 2 protons because in this case you have H2, so it's a diprotic. And if you look at your indicator, you also see that it is able to accept more than 1. So this one is C. Question number 7 of the numerical response. So we're looking to order from lowest pH to highest pH. So you're testing in bromothiamyl blue and in phenolphthalein. So our first one, if you're blue in phenolphthalein, you're going to be higher than 8.2. And if you're pink, you're higher than 10. So this one just is really telling us that you're higher than 10. The next one, if you are blue in bromothiamyl blue, you are higher than, what was that one? 8.2. I'm just looking at my notes here. I just might have to grab my data booklet again. And then in your colorless in phenolphthalein, that means that you're going to be higher than 7.6 and less than 8.2 because that's when you start to be colorless or you're colorless. In number 3, if you're green, that is showing you that you're right in the range for the buffer for that indicator for bromothiamyl blue, and then colorless because you're below that value that you would check there. And then number 4, doing the same thing. So bromothiamyl blue, you're higher than 8.2, but if you're light pink, you are in that range of 8.2 and 10, which would be the phenolphthaleins indicator. So once we've looked at those colors, then we can go from lowest pH to highest. So lowest would be number 3, and then we would go number 2, and then 4, and highest is 1. Okay, so a few more questions here, and then we'll take a break and I'll do the second part tomorrow. So question 21, you have some information once again, and this is telling you that some of the trees are being affected because of the acidity in the soil. So to solve this problem, some farmers are adding in some lime to the soil. So why would we do that? That would be because lime is a base and it can neutralize the acid, making the soil neutral so that everything will grow. Question 22. Which of the following substances in the above equation could be amphiprotic? So I think we've already did a question like this. To be amphiprotic, you're either water or you have a hydrogen and a negative charge. So you're able to act like an acid and a base. So definitely not A, possibly B, but we also have to see our other options. Not C because of the CH3O positive. And then same thing, D almost worked, but not because they're adding in that H3O positive. So the answer there would just be B. The next one, in comparison of the species, so because this is a weak acids only dissociate about 1%, meaning we'd have just a very small amount of products being formed. So in terms of what we have formed, we would not have a greater amount because there would be very little bit of this. It wouldn't be equal because there's so little of that. You would definitely have more acid than you would of the negative ion in the product. So it looks like the answer here is C. And we can double check. Yes, it's definitely not equal. So the answer is definitely C. And this very last one here, if you have a weak acid titrated with a strong base. So a weak acid titrated with a strong base, I'm just taking a look at my data booklet. It's going to change your equivalence point. It won't be at 7 exactly. It's going to be a bit below that. So the choices that we can have here, I think methyl red would be the best choice because that has a change around 5. So I would go with that one, but I'm going to double check that one a little bit later because it's the only one I did not double check. So as always, I hope you found this helpful. If you did, please subscribe. And if this is a review that you're following along with, please just know I'll have the second part up tomorrow. As always, thank you for watching.